Okay, David, take
Yes,
the Zoom
I
and
will
still
try
have
and
two.
share. Seems to be working.
Yeah. So David, Mark Riefel is very much interested in your talk, but he has to grade the final exam. So
Oh
actually,
dear.
he's now at the final exam.
Oh dear. Poor guy.
Yeah, because
Um,
it's 9:22 in the morning, and he is watching students writing an exam.
all right. All right. No rest for the wicked, I suppose.
Yeah, but he will definitely watch the recording. We still have 2 minutes.
Yep.
By the way, there's two things. One, I thought about it because George is here. So I think the final admission of Canada to these European networks has been done. I mean, from the point of view of European funding, Canada is now part of the Union. So this is quite a development.
So when you say Canada, what do you mean?
Well, Canada, the Dominion of Canada.
We can go anywhere in Canada.
No. That's not for us. Now, in the next, this is a perspective. In the next EU framework, Canada will be counted like Israel, like part of Europe.
Ah, okay, okay.
Okay, so that we can go to Canada anyway, and we do. Our final meeting is planned in the Fields Institute. And
Oh,
another thing is, which I very much hope for, Brazilian government seems to be acknowledging this European funding, and hopefully Gilles will procure some external funding from his government, just like we did with the Polish government. Yeah, because I have money to go to visit him, but I don't have money for him to visit me. I mean, I had it and I spent it. But for instance, he comes to Warsaw in January, and it's already problematic how to pay for his stay. Yeah. Okay. We'll still have 27 seconds.
can I use them to test whether going into
Yes.
full screen mode does it make the slides disappear?
Yeah, test.
Can you see my slides though?
We can see your slides, but not in full screen mode.
Okay. Anyway, I'll just keep them in non-full screen mode then.
4, 3, 2, 1, go. Hello, David. It's all yours. Take it away.
Thank you, Piotr. So what I want to do is to try to report on the work package that's called non-commutative metric geometry. And there have been quite a few developments over the past couple of years in slightly different directions. And rather than going into the details of one of them, I would like to try to survey sort of the main new discoveries. And just to set the scene, in the overall non-commutative landscape, we are in the lower right corner dealing with what Riefel called quantum metric spaces. And he introduced them some 25 years ago, and they are quite intimately linked with Kahn's non-commutative geometry, and I'll try to explain these things. But without further ado, let's get into the definitions. I'm not assuming that people are all that familiar with the theory of compact quantum metric spaces, so I will give some examples and some definitions, at least so that everybody is on the same page to begin with. So not surprisingly, you start out with a C-star algebra, and I will only be dealing with the compact case, so my C-star algebras will always be unital. And as the Gelfand correspondence tells us, this is a non-commutative analog of a compact topological space. And now the game you can play is to ask, how do you, on the non-commutative side, model the existence of a metric on the space in question, compatible with the topology, of course. And what Riefel realized was that this could be done by equipping your C-star algebra with a semi-norm, which is supposed to interact with the star in the obvious manner, being star invariant. And it is a slightly odd semi-norm in that it is allowed to take the value infinity, but other than that, it satisfies the usual axioms. Now, then this pair consisting of the C-star algebra and the semi-norm is called a compact quantum metric space if it satisfies a bunch of axioms, and they are appearing here in increasing order of importance. So the first axiom is that the semi-norm ought to vanish at the identity. So this already tells you that there is a big difference between the semi-norm and the usual norm. And in a second, I will explain why this is natural, because the first time you see it, you often find that this is a slightly odd criterion. The second axiom is that the domain, so the elements of the C-star algebra with the semi-norm is finite, has to be dense in the C-star algebra. So it's allowed to take the value infinity, but only outside of a dense subset. And then the last requirement, which is really the key point here, is that if you look at two states, mu and nu, on your C-star algebra, you can define a distance between them by running over the semi-norm unit ball and looking at all the differences that arise. So this is a semi-norm version of the usual norm on the dual space. And the claim is that this quantity, this DL, metrizes the weak star topology on the state space. So a priori, there is nothing preventing this DL from taking the value infinity, but if it metrizes the weak star topology, of course, this can't happen by connectedness and compactness of the state space. And now, if all of these requirements are satisfied, then the pair is called a compact quantum metric space, and a special name is given to the semi-norm. It's called a lib norm. For reasons that'll become clear now, namely, if you start out with an ordinary compact metric space and pass to the Gelfand dual, then of course you need to get one of these as an example if the definition is correct. And you do indeed by simply defining the semi-norm to be the smallest possible Lipschitz constant of the function in question. So this, of course, can be infinite if the function is not Lipschitz continuous, but it is clear already now that at least this guy will vanish at the unit, and also that it'll be star invariant. And it is classical that the Lipschitz continuous functions are dense in the continuous functions. So the second axiom in the definition is also satisfied. That this quantity in the third condition actually metrizes the weak star topology requires a little bit of work, or a reference to some classical literature. You can find it in some papers by Kantorovich and Rubinstein from the 50s, formulated in a different language, of course, but that is really what they prove. So you have this very natural passage from the class of compact metric spaces to the non-commutative analogs to the compact quantum metric spaces. But you're, of course, also interested in non-classical examples, so let me give you a few here. So one thing you can do is you can take an ordinary group, let's say a compact group, and let's say that is a compact metric group, something like the circle would do. And then we let it act on a C-star algebra in an ergodic way and in a strongly continuous way. So the ergodicity just means that the only element that is globally fixed by the group is the unit. Now you can then cook up one of these lib norms for the C-star algebra by simply mimicking the idea of the Lipschitz constant from before. So you, instead of taking the absolute value, you take the C-star norm difference of all the moved elements and you divide by the distance function between the group element in question and the unit element in the group. And then you soup over all these quantities, and Riefel proved that this gives you a lib norm. And therefore, it gives a compact quantum metric structure. And it should be said that in this line of business is not so much a matter of discovering whether or not a C-star algebra is a compact quantum metric space, but to find an interesting lib norm, something that carries some geometry of the C-star algebra in question. Maybe this was not so clear, but what I'm trying to say is that there are non-commutative metrization theorems. So as long as your C-star algebra is separable, you can always find such a lib norm on it. But the question is whether you can find one that somehow is reflected in some already existing geometry or topology on the C-star algebra. So here it is a lib norm that somehow captures the action of G that exists on A. And you can do many examples along these lines. You can do matrix algebras. So if you take SU2 and take an irreducible representation in dimension n+1, then if you conjugate with these group elements, you do indeed get one of these ergodic actions of SU2. Or if you look at the non-commutative torus and you start rescaling the generators with the ordinary torus, you also get one of these actions. So this already gives you some interesting non-commutative examples, and I will show you in a little while how you can also obtain examples from spectral triples. But before doing so, I would like to digress a little bit and talk about one of the key features of this theory of compact quantum metric spaces. Because one of the things that makes it particularly interesting is that you have an analog of the classical Gromov-Hausdorff distance between compact metric spaces. So the situation is that you can define in a very natural manner a distance function between compact quantum metric spaces. So it makes sense to ask whether two such compact quantum metric spaces are close or far apart. And it opens up the possibility for studying this theory from a much more analytic point of view. So you can now talk about whether a sequence of compact quantum metric spaces converges to another, or you can ask whether a certain one parameter family varies continuously in the parameter. So all these kind of questions are now well posed and can be attempted answered. I will not go into the nitty-gritty details of the definition of this distance function. I just want to remind you how the classical Gromov-Hausdorff distance is defined, and then try to use this as a stepping stone for an analogy. So imagine that you have two classical compact metric spaces, M1 and M2, and I imagine them already being embedded into a third, the plane of the slide. And then the Hausdorff distance between them is the smallest r, so that one space is contained in an r neighborhood of the second, and the second is contained in an r neighborhood of the first. So it's an infimum. And then if the two spaces are not already embedded, you make another infimum over all possible isometric embeddings, and that is then the Gromov-Hausdorff distance. And this is a very classical thing, and it was used heavily by Gromov. It featured in his famous polynomial growth theorem. So this is an important quantity in classical geometry. Now, on the quantum side, you can formulate things purely based on the quantum metric spaces itself, but you can also phrase the distance function in terms of the state spaces. And whereas in the classical case of just ordinary metric spaces, we take an infimum over all isometric embeddings, for the quantum Gromov-Hausdorff distance, you need to take into account the convex structure of the state spaces. So you take the infimum only over affine embeddings into norm spaces. But this gives you a perfectly good distance function with which you can study these quantum metric spaces. And it was exactly this distance function that made Riefel able to show this by now very famous result that the matrix algebras converge to the Tooth theorem. So this was putting into a rigorous mathematical framework, something that physicists had been doing in a slightly less rigorous fashion for years. And I think it's fair to say that this result was the claim to fame for the quantum Gromov-Hausdorff distance. And there has been a lot of research in this direction over the past 20 years or so. Various refined version of this quantum Gromov-Hausdorff distance has appeared, and names to be mentioned here are David Kerr and Han-Feng Li, and certainly Frédéric Latremoilière, who has an entire, quite extensive body of work on this stuff. But I wanted to also touch upon how these compact quantum metric structures play together with Kahn's non-commutative geometry. So if you imagine that you have a spectral triple, so a non-commutative differential structure, I'm sort of, by the way, I'm sort of assuming that I don't need to define a spectral triple, but in general, I can't see all of your faces at the same time. So if I say something that you find unclear, appalling, or straight up wrong, just interrupt me as I go along. So a spectral triple, I think I might say something about it anyway, consists of three objects, an algebra acting as operators on a Hilbert space H, and then there's this unbounded operator D around, which is mimicking a differentiation operator in the commutative context. And one of the basic axioms for such a spectral triple is that the elements of this algebra curly A have to preserve the domain of the unbounded operator, and the commutator, which is then well defined, has to extend to a bounded operator, which means that I can take its operator norm, and this assigns a number to the element A, and this is going to be my semi-norm. And outside of this curly A, I'm just going to declare it to be infinite because I'm allowed to do so. So the domain of this semi-norm is by definition the smooth algebra A for the spectral triple. And what one could imagine that I would say now is that you always get a compact quantum metric structure in this case, but it's not the case. So it's sometimes the case, but not always the case. And this is maybe a little bit strange from a philosophical point of view, in that if you really believe that a spectral triple is a non-commutative analog of an even very nice Riemannian metric, then it should give you a non-commutative metric structure, but it's just not always the case. For instance, because it can be the case quite easily that the Dirac operator commutes with much more than just scalar multiples of the identity. And as soon as you have this situation, you can always find states that are infinitely far apart with respect to this metric. And if you can find states that are infinitely far apart, there's just no way that this metric or extended metric will metrize the weak star topology. So there's a very immediate obstruction to this being the case. And you can also find examples where this immediate obstruction is not there, but nevertheless your semi-norm here does not give you a compact quantum metric structure. It's just a very subtle thing, it turns out. And I think it's fair to say that one of the most important questions in this connection is, can one characterize when you get a compact quantum metric structure in terms, of course, of the non-commutative geometry of the spectral triple that you're studying? And I don't know the answer to that. So if you are looking for a good research question, here's certainly one. I'm not even close to having an answer. So I think it's a very open question by now. And just to add insult to injury, even if you take a C-star algebra that you somehow feel that you understand reasonably well, for instance, a group C-star algebra, and if you want to give this a Dirac operator, it's a classical thing that if your group has a length function on it, you can turn this into a Dirac operator by simply rescaling the basic, what is it called, the orthonormal basis elements with this length function. And this is one of the very first non-commutative examples of spectral triples. And if you don't know these length functions, just imagine that your group is finitely generated, and then you take a finite generating set. And how is this length function defined? Well, you just take your group element, you write it out in the generators, and then you look at the shortest possible word that you can use to describe this group element, and this is your length function. So this is the example to bear in mind. You can do things more generally.
David,
yeah.
I might interact.
Absolutely.
Interrupt for a second. Interacted by interrupt and interact. Can you have some answers to your question more determined when you assume some special cases, like, I don't know, A being commutative or A being finite dimensional, just some stupid assumptions?
I don't know. I don't know.
So even in some very simple cases, you might have these semi-norms giving or not giving compact quantum metric space structure.
I can, what I can give you is, I can give you commutative examples where it fails.
All right.
About finite dimensionality, I haven't really thought carefully about it, so I'm not going to make any bombastic statements. But of course, I mean, if you assume enough and commutativity, then you are under the bracket of Kahn's reconstruction theorem, and then you should be good, right? Because then you are really coming from a Riemannian or a spin manifold. So, but these are like, assuming commutativity is of course also very strong.
Andre, you did a lot of work on finite spectral triples. Would you care to weigh in?
Well, finite spectral triples are sort of, I would say, maybe boring. So finite in the sense when the algebra is finite.
Yeah.
I think, you know, I think, you know, I mean, in the case of finite groups, for instance, and finite spaces, everything is sort of trivial. David?
Yeah, but it's not clear to me that this will be a compact quantum metric space when A is finite dimensional.
Good question. But I mean, my intuition is that it would be, but
No, but there is the simple
I haven't seen it
condition.
proved.
You
David?
just...
So you can reproduce this thing that certainly you can do finite dimensional examples where the Dirac operator commutes with more than just the scalars. So
Yeah.
so the question is whether this is the only obstruction in the finite dimensional case.
Yeah, but this we know, it is the only obstruction. It is
Okay.
in several papers. It's a small remark, but you can find also the proof, because basically you have on a finite dimensional C-star algebra that is finite dimensional vector space, and there is only one topology induced by a norm. So you use this fact that topology is unique on the dual level of states, and then you are done, basically.
Yes, right, absolutely.
Yeah.
So that is so the trivial obstruction is the only possible obstruction in the finite dimensional case.
And I think this remark is also in some paper by Mark. I'm not sure. I am sure that is in a couple of my papers with
Very
proof.
good. Very good. Okay, so it's settled there, and it is not at all clear in the commutative case. Is
But
the
also,
statement.
sorry, one more comment on the finite dimensional case, because Mark Riffel gave a very nice talk in June where he proved that I don't know how general I was, because I don't remember, because he was talking about his last paper on this connection with what was well, I don't remember the application, but he showed that the quotient semi-norm, when you quotient by multiples of the unit element, that is always induced by Dirac operator. So it's kind of inverse result. You have a compact quantum metric space, look at the quotient semi-norm, and you always have Dirac operator. Then I don't know how general it is. If behind the finite dimensional case, you can say something, I don't know.
Right. I'm a bit on Andre's side here, that the finite dimensional case I haven't really paid much attention to, considering it's sort of like a slightly degenerate case. But of course it's the right place to start. If you have more questions than answers, you need to sort of scale down the
Exactly.
complexity.
That's why I asked my question.
And I always have more questions than answers.
Well, I mean, the next class would be approximately finite dimensional, but I'm sure that there is a lot of stuff on that in the literature.
Yeah. But it's a good direction of trying to answer David's question.
I think there are at least many ways you can attack this question, and I would be interested to see even partial answers. But just to give you some positive results and not just open questions, in this group situation, you can even, it's even unclear. So you can prove that you do get a compact quantometric structure if your group is hyperbolic or of polynomial growth, and the two arguments are completely different in nature. And it would be also interesting, and this is also something that Riefel pointed out some years ago already, to find one proof that covers both. So the conjecture is, or the hope, I suppose, is that you can do something like groups of rapid decay, which is the first natural group, class of groups encompassing both the hyperbolic and the polynomial growth case. So this is what you can do. And so this is just to sort of give you an indication of the fact that whether or not you get a compact quantometric structure is a very subtle thing. I think, by the way, just to underscore the point, that as long as you stick to word length functions, at least, there are no counterexamples whatsoever of these length functions giving a compact quantometric structure. So a counterexample would, of course, also be extremely interesting. And things, of course, only get worse if you allow yourself to enlarge the scalars. So you can, if you wish, think of a group C-star algebra, reduced group C-star algebra as a cross product with the base algebra being the scalars. But it's very natural, of course, to also ask, what about non-scalar bases? So the question more formally is, imagine that you have a compact quantometric space and that you have gamma, the group from before, acting on A, and that the length function that we have given our group does give you a quantometric structure on the reduced group C-star algebra. When can you fuse the two compact quantometric structures into one for the cross product? And this is also, it turns out, a difficult question to answer. And most of the positive results so far have quite heavy restrictions on the group. So most of them deal with gamma simply being the integers, or the best possible case so far is virtually abelian. But still, it is fair to say, I think, that the restrictions on the group side are quite heavy. But if you look into the literature here, what is going on is not so much a merge of a compact quantometric structure on the integers with the one on A. It is more so using that Z is in general a very nice and easily understood group in order to lift the semi-norm LA to the cross product. And what we decided to do, we being Ara Austad, our postdoc, myself, and Jens Kyed, we tried to see whether you could do something differently. Namely, imagine now that I have one of these groups from before where I know that the length function gives me a compact quantum metric structure. Can I utilize this information in order to merge it with the semi-norm LA? And what we were able to prove is that you can construct a very natural semi-norm. I've written it up here, and there are several components. One taking care of the base space direction, so the algebra A direction, and one dealing with the group direction. So I boost the differential, the DL to the cross product Hilbert space, and then I just take the commutator and the norm. But this in general has a huge kernel. So I need to add more in order to get a reasonable semi-norm. And what I just do for an element in the algebraic cross product is I just take the soup over all the semi-norms that appear when I range over the Fourier coefficients of this cross product expansion of my element. So this is the second term, and the third term is just to make sure that the semi-norm that I build is star invariant, because this was part of the requirement. And I haven't made any assumptions saying that the group should act in a semi-norm preserving manner. And if I don't feel like adding these kind of additional assumptions to the setup, I will need to include this just to have a semi-norm which formally fulfills the requirement of being a compact quantum metric space. And what we checked was that this does indeed work. It gives you a compact quantum metric structure, and it gives you a natural class of examples. So let me just keep an eye on the time. 15 minutes or so left. So really what is going on here is that we are able to prove it for amenable groups for which we know that the gamma, the C-star reduced gamma, is a compact quantum metric space. But given that all of the amenable examples that I know are those of polynomial growth, I've phrased it like this. But this is to say that it is really the underlying amenability of the group gamma that is the driving force here. And it is unclear to me, at the moment at least, how to get rid of the amenability assumption. So there's another good open question there for one to investigate. How can you take these kind of ideas and make them work in a non-amenable setting? But
say amenable, you mean gamma, right?
gamma, yeah, it's on gamma. What we're really using heavily all the time is that the trivial representation extends to the C-star algebra. So this is a distinguished state that we can use, and we use it heavily. So without amenability, the argument clearly breaks down. But
And let me ask you an obvious question for me, because for me this cross product is nothing but a trivial compact quantum principal bundle, because gamma is discrete, I presume, right?
yeah, gamma is
If gamma is
discrete, finitely
discrete, then
generated.
simply its Pontryagin dual is a compact quantum group. And what you're having here is a trivial compact quantum group principal bundle. So would you fathom any ideas of how to derive a compact quantum metric space structure from a fixed point C-star algebra, compact quantum metric space structure, and the compact quantum group compact quantum metric space structure? So fiber and base. Could you then somehow, knowing intrinsically the topology of a bundle, recover or construct, maybe not recover, but construct the compact quantum metric space structure on the total space of a total quantum space bundle? You know what I mean?
That you can do certainly in some cases. We've done it for SUQ2, and there's a very recent paper by Jens Kohl who's doing quantum circle bundles. So, but I'll get to that in a slide's time or so. But yes, but not in full generality where you just have
Okay.
yeah, not in full generality. yet.
Also, I believe that Bram Meslan and Branimir Čačić were touching upon it. So
Yeah, I think
did
so.
some
I
work
think
in
so.
this.
Yeah,
Right, Bram?
yeah. I don't remember the name of the paper. Yeah.
Well, yeah, we didn't touch compact quantum metric space there, but we
Bram, you're here. Hi.
Yeah, but you did spectral triples, right?
principal spectral triples, we factorized, so it was more the other way around. We had something on the big algebra and then factored it in Kasparov theory into two pieces. So that's a different idea from lifting something from, say, the fixed point algebra to the whole space.
Okay.
So we started with something on the whole space.
Okay, I've got you. Thank you.
Excellent. Other things to be discussed before I move on? All right.
Move on.
I'll move on. So you can of course, you can of course argue that you don't like this semi-norm that I have shown you here. You might find that it is not a natural thing. But I would like to try to counter such a potential argument by showing you how you can really get some genuine geometric information from this kind of result. So the thing is that if you imagine that the semi-norm on the compact quantum metric space that you started out with also comes from a spectral triple, then you have a spectral triple on A and you have a spectral triple on gamma, then it's very natural to look for a spectral triple on the cross product. And this is actually those references that I gave you before very much deal with exactly this situation. But in general, you need to add more assumptions. And this has been known for a while. This is not our results. You need to add something, some extra data on the action of gamma. And what you really need is, well, you need first and foremost that the action preserves the smooth algebra. But this is presumably something that people will not object to in general. But then you need a condition which is called metric equicontinuity. And it's stated here. So it means that if you start moving an element around with group elements and looking at these commutator norms, they should stay bounded. And this is, of course, a somewhat more substantial requirement. And but if you assume this, you can fuse the Dirac operator on A with DL to obtain a spectral triple Dirac operator on the cross product. So this is genuine non-commutative geometric information, and we could also prove that under the same assumptions and the assumptions above, so that the Dirac operator makes sense, then this gives you a compact quantum metric structure. And we do this by simply proving that this semi-norm coming from the new Dirac operator is, and I need to get the inequality right, it is bigger than the one from the previous slide. Because the smaller the semi-norm, the harder it is to be a compact quantum metric space. So it follows with some additional work that this Dirac operator gives you a compact quantum metric space structure. So I think this is what I wanted to say on cross products. And now in my last couple of slides, I want to change attention to Q deformations, because there has also been quite a lot of work in this direction recently, and I'd like to give you the highlights there as well. So so Q-deformed spaces is very, very classical in Warsaw, and it is a very rich source of non-commutative structure. But it turns out that these Q deformations are hard to get to interact well with spectral triples, with Kahn's non-commutative geometry, because there are these sort of twists around that seem to be just an integral part of the structure, which means that if you're suitably Q-deformed, you're unlikely to be particularly willing to allow for spectral triples. But you can get fairly far as non-commutative metric geometry goes, and this is what I'd like to show you now. So the point of departure is as always the spectral triple on the Putty sphere introduced by Dabrowski and Sitash. So the Putty sphere is a non-commutative analog of a two-sphere, and it is not so badly Q-deformed that it will not allow for a genuine spectral triple. And Dabrowski and Sitash found such a spectral triple, sort of revealing part of the non-commutative geometry of the Putty sphere. Now, it turns out that the spectral triple is very compatible with the non-commutative metric geometry in that the semi-norm that thank you, Piotr.
Sorry, I couldn't resist it.
There was an accent that accidentally went over the E and should have been over the
Yeah,
S.
because not an accent, it's just a different letter. It's sh.
Yeah. I misplaced the slash in my text file.
But congratulations on Dombrowski. This is perfect.
Yeah, thanks.
But by the way, now I have a question. Is your point the following? That because I find it very interesting conceptually, then when you do Q deformations, some of these Q deformations screw up the smooth structure, and it's harder to get the spectral triple, but they still are decent metric spaces, but not like Riemannian manifolds. Would it be?
Yeah, this is part of the point, I think, that I wanted to make, that if you're a little bit more flexible and only ask for non-commutative metrics rather than non-commutative differential geometries, you can get slightly further, because you can allow for these twists to appear, and you can have sort of take twisted commutators in one direction and untwisted commutators in other directions. Whereas if you were to sort of assemble everything into a spectral triple, it would be neither nor, because it would somehow be untwisted in one direction and twisted in another direction, which is it seems, and this is just my intuition, it seems that this is sort of an integral part of these Q deformations, something that you need to just take seriously.
Yeah.
But
Yeah, thank you.
But you're welcome. So from the point of view of metric geometry, these are really nice in that they are compact quantum metric spaces, and they vary continuously in the deformation parameter Q. So you have, in particular, that they will converge in Riefel's Gromov-Hausdorff distance to the classical two-sphere as Q tends to 1. So every time you look, this is Jens's slogan, every time you look at a classical sphere, you should know that arbitrarily close to it sits a little quantum sphere. You just don't see it. And we were able to lift these things to quantum SU2. It requires quite a bit of work, but quantum SU2 can also be given a very natural compact quantum metric structure, and it'll vary continuously in the deformation parameter. In particular, it'll converge to classical SU2 with its round metric coming from identifying it with the free sphere. But you can see that these are very low dimensional examples, two sphere, free sphere, these kind of things. But and last time we met here, the higher dimensional spaces were completely open, and there's been quite a bit of work on that. So let me end the talk by mentioning that. So the general picture is a little bit more general. So you don't just have the Putty sphere and the quantum SU2. You have a tower where the smallest algebra is a complex projective space sitting inside a Q-deformed odd sphere, sitting again inside a suitable quantum SU2. And when L is 1, the rightmost part of the tower is the Putty sphere, and the two other things are identical. So the tower is smaller there. And what Jens Kuhl and his PhD student Max Holt Mikkelsen proved was that the spectral triple, so the complex projective spaces, also have spectral triples introduced by the Andrea and Drobowski, give you a compact quantum metric structure independently of the dimension, so in all dimensions L. And in a separate paper by Jens alone, treating these bundles that we talked about before, he shows that these compact quantum metric structures can be further lifted to the odd dimensional spheres. So this is where
Sorry,
things stand
I
right
have,
now. Yeah.
I have an immediate question. Sorry to interrupt. Is it this paper of Jens Kyed from 2024 where he was doing the proof that these Waxman-Soibelman quantum sphere sister algebras are graph sister algebras? My question is mostly for Francesco.
I don't think Jens proved that they were graph C-star algebras.
Yeah, I mean, I know that this is Hong-Szymański, but I know that there was a long discussion about the proof, and I know for sure that Jens Kyed was involved, but I don't remember the details. Francesco, are you there? Okay, he's not. Okay, sorry
All right.
for interruption, but
No problem.
But somehow you see, I see the name, the date, and the object, and it seems to me very likely that this is where there was this debate of a proof that these are graph sister algebras settled.
Yeah, I don't think so.
No?
But
Okay.
I should check up on the details of the
Yeah.
paper, of course. But I think the main point of the paper is that you cannot get spectral triples. I think he called them sort of spectral quadruples or something like that. Some more general things that will still give you, even though they're not spectral triples as such, they will still give you a compact quantum metric structure. And what is, I mean, there are many questions left open. So one thing is, of course, how to deal with SUQ in higher dimension. This I don't know. And also, at the moment, we are trying to muster the courage to attack the convergence issues for these things, because it's very natural to assume that these complex projective spaces these Q-deformed complex projective spaces will converge to an ordinary projective space as Q tends to 1. But that is I'm not going to call it work in progress because we haven't really started yet, but work to hopefully be in progress soon. So I think I have 1 minute left, so I think it's best to stop here. Thank you so much.
Yeah, thank you very much. So let me immediately proceed to questions. Could you please go back to the previous slide?
Yeah.
Okay. So my first immediate question is, would you somehow measure the distance between, I mean, first, it's all the time just Waxman-Soibelman quantum complex projective spaces. But we recently, with Francesco and Tomek and Albert Schuh and Bartek Zieliński, we unraveled a non-commutative CW complex structure of multi-push-out quantum complex projective spaces, which are somehow far more complicated and maybe interesting than these Waxman-Soibelman ones are. Even computation of K-theory required Richard Nest, and a brilliant idea of him to do it. Now we understand it, and from a hindsight, it looks simple, but we were stuck for a number of years, even not being able to determine the K groups. So these are much more complicated combinatorial sister algebras. However, there seems to be some, clear geometric relation between the two sister algebras. We have morphisms in our category between them. Well, they are homomorphic to invertible on K theory, and that's all we care about. And I was wondering if somebody could somehow measure the distance between this multi-push-out quantum complex projective spaces and Waxman-Soibelman. So that would be very interesting to see. I mean, you can go into the simplest case, L equal to 1. By the way, that's not a good idea to use L because it looks like 1. I mean, when I first look at it, oh, it's CP1. Okay.
I see.
mean,
I see. I
L is
could have made
tricky.
it. I could have made it curly, but then it would look like the length function from before. I'll yeah. Point
Yeah,
taken.
it's just a trivial remark, but it's later on when you have 12 plus 1 is obvious, but when you have CPL, oh, it looks like CP1. Anyway, you can just take that CP1, the standard Podleś quantum sphere, and you can take the mirror quantum sphere, which we have with Wojtek Szymański and a bunch of others. And then this is the lowest dimensional multi-push-out quantum compass projective space. And that's the Podleś. And look, basically you obtain one from the other by collapsing one quantum disk into a point. So there is some shrinking involved. It's not a homotopy, but there is some shrinking involved. And I will be very curious to see how far away these spaces are from each other, because it's like a phase transition. It's not, you know, the Teplitz algebra remains Teplitz algebra until it becomes a point and it jumps, you know, and the size doesn't change anything topologically. So there is some phase transition, and so I cannot imagine, you know, approximation in any reasonable sense. But maybe I'm wrong. Definitely, it would be nice to see the distance, this quantum Gromov-Hausdorff distance, whatever it's propinquity, whatever Frederick invented. Can it be measured? This would be very, very interesting for me, even in this lowest dimensional case for L equal 1. So that's my first question.
Is it at all
And
clear that these more generalized things are compact quantum metric spaces?
no, not at all. And
So you will
maybe
need to start there and then measure the distance once you know that the
yeah,
distance makes sense. Yeah, so
yeah.
it's a non-trivial matter, presumably, to pursue this idea.
Yeah, of course you're right. I should have started from mentioning this. Yes, and so that's something which would be really, really nice to tackle. And my second question is kind of obvious. You know, many of these guys are graph sister algebras or higher rank graph sister algebras. So what can you say about the non-commutative metric geometry for graph sister algebras?
Wish I knew. I
Oh,
don't know. I don't know.
but wasn't it Konrad Aguilar who was your postdoc in Odense for 2 years, and he did some work there?
Yeah. I mean, but I think it's. Oh, yeah. I don't remember the results of the paper, but I know that he worked on it. But I also am not. I think it's somewhat specialized still. I don't think that if you just give me a graph and construct
No.
its I can say nothing for the time being.
Okay, Ralph, go ahead.
Oops. Ralph
I
was
somehow
muted
cannot
again.
hear you.
Jonathan.
Did Ralph disappear?
Yeah, it seems that Ralph disappeared.
He's still there.
no,
I
he's-
just think he's trying to figure
Yeah.
out his microphone situation.
I see. But did you also have a question?
I did, so maybe in the meantime I'll take this up. Thanks for lovely talk, David. I wanted to ask, you mentioned this relationship to, well, in the cases where you do have positive results for the cross products and quantum metric space structures on those.
Yep.
You just before that you had mentioned this kind of, you have this nice case for certain or some very nice tractable groups and then also hyperbolic groups. And you mentioned the phrase rapid decay, which triggered a little spark in my mind, mostly because I've been working on it recently, but often the groups, or the C-star algebras of groups that we know that have stable rank 1, we often use rapid decay to prove this. So is there any relationship that you can speak to between the stable rank, or is this more of a rapid decay kind of phenomenon? And is there any possible way to go in the future for the cross-product structure there?
Ooh, yeah. The short answer to your question is I have no clue. The slightly longer answer is that I am very curious to learn about any sort of inherent C-star algebraic property that is, say, preserved under very small distances. I don't know any of these perturbation results. Like, say, one space has property P and it's like just epsilon away from another one. Is there any chance that property P can be, transferred? These kind of questions I would really like to know answers to. And yeah, as you can see from some of the results here, the Putlish sphere can converge to a classical two-sphere, so you can be very, very close to a commutative thing without being commutative, for instance. So yeah. But this was
Sure.
not so much as of an answer as it was just hitting you back with another question. But this is the best I can do at the moment, I fear.
Oh, great. Thank you very much anyway.
You're welcome.
Yeah, thank you, Jonathan. So now I can read Ralph's question, okay?
Yeah.
It's in chat.
Yeah, and I think now I can speak again,
Oh,
right? I
okay,
left the
good.
audio.
Hi,
So I was wondering whether anybody here knows about writing these quantum spheres as cross products by partial actions. Let's say Z to the L or something acting on something commutative. I think that should be true, but I haven't seen it, but it might well be known. So you have this, they are kind of graded in a canonical way by just taking the coordinate directions and counting degrees there, I think.
But I think that if this is true, it should be a more general property of graph sister algebras, because the big commutative degree zero part is just the diagonal subalgebra of the graph sister algebra.
Yeah, you could do this also for some special graphs if you just you can, besides the usual obvious gauge action, you might have more interesting actions of larger tori, just giving different degrees to different edges.
Yeah.
Yeah, and well, I have one doctoral student who is looking at some parted from star algebras to C-star algebras, and they seem to be examples where this might be relevant. And it would be nice to know for her whether this is already done or not, whether it's worth to look more into this particular class of examples.
Unfortunately, I don't know.
That's fine. If nobody knows, then it's worth looking into, that my student can
Yeah. I guess that answered your question.
look into this more carefully. But if anybody knew about it, I would have to look into what's already known about this.
Of course. Okay, so David, thank you very much. And I'll stop recording.